We're now going to dive fully into convolutional neural networks and discuss all their components. So we'll start with the central component, the convolutional layer, and we'll discuss zero padding, which essentially allows us to modify the behavior of the convolutional layer. We'll talk about pooling or downsampling, and then flattening, which just rolls out the convolutional layer to a vector so that we can work with multi-layer perceptrons again. So convolutional neural networks have been proposed by Jan de Kuhn et al. 1989, and they use extensively 2D convolutions, and they are currently state-of-the-art in image classification and also other tasks. And this actually started really off in 2012 by a paper by Krzyzewski et al. Designing LXNet, a particular type of convolutional neural network, which set new state-of-the-art in image classification. So let's get started with the central component in convolutional neural networks, the convolutional layer. And so the basic principle in ConvNet is that we are working with feature maps. So feature maps have locality, and at each location we might have several features or channels. And so the feature map we're starting with is essentially just an image. So here we have an image of 32 times 32 pixels, and it's an RGB image. So we have three channels: a red, a green, and a blue channel. And so yeah, we're starting off with this image of dimension W0, H0, and Z0. So here, W0 and H0, the width and the height are 32 times 32 pixels, and we are using three channels. And so we are, ConvNets like MLPs work in layers, so we are just transforming these localized feature maps. So the image is interpreted as a localized feature map, and at each location we have three features, so just the red, green, and blue values. And so we are starting off with this feature map, and we're just transforming this the feature maps into other feature maps. And so yeah, the image is interpreted as this zeroth feature map H0. And now we are going to apply a convolution, and for this to this end we will use a convolutional kernel, which is a tensor or an array of shape k1 times k1 times c0. And K1 is actually just the window size or the width of the kernel. So, and in this example, we assume K1 is 5. So this is a window of 5 times 5. And we need as many, we have three channels, and therefore we have the third dimension is Z0. And the way to interpret this is essentially that this three-dimensional tensor, this kernel, is actually just an array of matrices. So we have so a matrix is, each matrix is K1 times K1, and we have one matrix per channel. And therefore we end up with this three-dimensional array or tensor K1 times K1 times C0. And now we are applying a convolution to our image, a 2D convolution. And if you're now slightly confused, so in the last section we introduced convolutions with grayscale images, and we had that the kernel was just a matrix. And if we want to, if we want to apply a convolution to this RGB image, it's actually just working that we apply a convolution independently to each channel. So we have three channels: red, green, and blue. And so so the sum runs from 1 to 3, so red, green, and blue. And so the input image is actually also is a three-dimensional tensor, 32 times 32 times 3. And this notation here essentially just reads out the seized index. So C runs over the channel. And so for each C, this is essentially just one of the channels. So red, green, or blue, depending on C. So we're looking at the channels independently and convolving it with the respective kernel. So this is a 32 times 32 matrix, and this is essentially a 5 times 5 matrix. And we're iterating over channels and essentially applying convolution to each channel independently, and then we are just adding the result. So each of these terms will be a matrix, and we're just adding these matrices. And we are also adding a bias term. So like in multi-layer perceptrons, we had this bias term, and we also add a bias term here. So yeah, we have this kernel, this orange kernel, and this yields now a new feature map. So so this convolution essentially extracts a new feature map, and this new feature map will be of shape 28 times 28. So this is now a smaller feature map. So we started off with 32 times 32, and now we got 28 times 28. And the reason is because we had a filter size or kernel size of 5. And now if we just move this 5 times 5 kernel in here, we're essentially cutting away 2 pixels on each side. Or actually, so that we need to fit this kernel within this image, and so there are only 28 times 28 different positions where this kernel won't get out of this image. So we will, therefore this is now a reduced size of this feature map, and in a few minutes we will discuss zero padding. So essentially just adding zeros outside this image will allow us to keep us the same size, but not for now. Let's just consider this convolution which reduces the size. Okay, so we have this convolution. This generates a new feature map 28 times 28. So this is fun, and so why not have more fun and now apply a second convolution with a second convolutional kernel. So this this blue one here. And so first we had this orange kernel and performed convolution. Now we take a separate kernel, this blue kernel, which has different parameters than the orange one, and which will produce a different feature map, also of 28 times 28. And we just stack the result to 2 channels. Now we have 28 times 28 and 2 channels. But what we have done 2 times, we can do 3 times. So we can add another kernel and perform another convolution and just stack it here. And now we have essentially 3 channels in this new feature map. And maybe we just do this in total 6 times, or generally Z1 times. So Z1 is the number of output channels. So we started with 3 channels RGB, and now we've produced 6 output channels by just applying 6 different kernels. And so generally this number of output channels is a hyperparameter. And each of these kernels produced a feature map, and so each of these different colored kernels produced a feature map, and by stacking them, we got W1 times H1 times C1 feature map. So here in this example, W1 and H1, the width and the height of this new feature map is 28, and the number of channels 6, because we applied 6 different convolutions. And so this new feature map is now called H1. So recall the first feature map, the image was called H0, and now we've produced essentially a new feature map, H1. Yeah, so each of these channels here was produced with one of these kernels. So the color here corresponds to these different channels, and each of these kernels was 5 times 5 times 3. We also had these bias terms. To each of these feature maps, we added a bias. So let's just quickly go back. So this here, so we added this bias. So we performed convolution with each of these kernels and had the bias. So in total, we will have now 456 trainable parameters. So we have 6 output channels. Each of the kernel has 5 times 5, has size 5 times 5. We have 3 input channels, and we have a bias term. So in total, this gives 456 trainable parameters. Now we had these 6 different kernels, and so each kernel is a 3-dimensional array. We can just now stack them to a 4-dimensional array. So each of these kernels are 3-dimensional, but we have 6 of them, which is effectively a 4-dimensional array. So we're just packing these different kernels into a 4-dimensional array called W1. So W1 for the first layer. So this was the 0th layer, the image, and the 0th layer is the image, and the first layer is now this transformed feature map, and the parameters are W1 and B1. So W1 contains all these convolutional kernels, convolutional kernels, window size, number of input channels, and number of output channels. And the biases are collected in a C1 dimensional vector B1. So C1 is the number of output channels here, 6. And yeah, formally to go from our input image, so the zeroth feature map, H0. So again, each feature map is essentially a 3-dimensional array. So the zeroth feature map is 32 times 32 times 3. And the second 28 times 28 times 6. And formally to go from the input feature map to the output feature map, so from H0 to H1, we do this. So we take, so D is now the output channel. So D is the output channel. So we take now this. So if we fix D, this will be a 3-dimensional tensor. If we fix C, this will be a matrix. So for each D, we apply this convolution, this multi-channel convolution, and add a bias term. So this is formally how we go from the zeroth feature map to the first feature map. And yeah, we use this Pythonic slice notation here. So colon CD. So the W1 is a 4-dimensional tensor. And we fix C and D, then this will be essentially the first matrix slice, the K1 times K1 matrix. Yeah, great. So this is how we transform. So this is the convolutional layer using this 4-dimensional convolutional array and bias vector. And now, yeah. So this is so to introduce some naming, we call this a K1 times K1 times C1 convolutional layer. So K1, the filter size, and 6, the number of output channels. And so in the naming, often the number of input channels is omitted because this is anyway given. And essentially we say, well, we take this image and we apply a 5 times 5 times 6 convolution, which means window size is 5 and the number of channels is 6. Yeah, we are working with neural networks, and therefore, after having computed this convolutional layer, we apply an element-wise nonlinearity, for example, a ReLU or sigmoid or whatever. So this is a spatially organized feature map, and this nonlinearity just acts element-wise. So we have this feature map, and this phi just acts on each of these values here. And so we feed in a 28 times 28 times 6 feature map into phi, and the output is just, again, 28 times 28 times 6, but to each entry, phi was applied. So this works, the phi works element-wise, so we still have this feature map. And now, essentially, we just repeat. So we've transformed one feature map, the image, into this feature map, and then just applied an element-wise nonlinearity. And now we can just repeat this. So essentially, we started with an image, and we transformed it into some kind of abstracted features which are still localized, and then we applied a nonlinearity, and now we can just again apply another convolutional layer to get another feature map. So, and here is a little question. So to go from a 28 times 28 times 6 feature map to go to a 24 times 24 times 8 feature map, what are the dimensions of our parameters here? So just as a hint, so in the first step, we had to cut away 2 pixels on each side. And here, so how many pixels did we cut away here? So this gives you the window size, and the number of channels is obvious from this image. So as we've just seen, applying convolutional layers to our feature maps reduces the size, so the width and the height. And if we want to avoid this, we can apply zero padding to the input. So essentially just extend the input with enough zeros that we keep the same size. And so in particular, if the kernel size, so the window size k is odd, then we just need to pad with k over 2 floor many pixels on each side so that we get the same size. So here's an example without zero padding. So we have a 4 times 4 input. And here we are only considering a single channel, so to keep it simpler, so only a single channel. So we have this 4 times 4 input, and we're applying a 3 times 3 convolution, so k is 3 here. And if we don't apply zero padding, you see that the output essentially becomes smaller than the input. So because if we move this 3 times 3 window, so there's the first position where it fits in is this, the second position here, but then we are stuck on the right-hand side, so we move down here. 3 and 4, and these 4 positions correspond to the output image. And now if we want to have the output image has the same size, we need to zero pad. So this is the K is 3, so we can pad with K 3 over 2 is 1.5, floor is 1. So we just need to extend each side with one black pixel. So if we do this, so we now zero pad, and now we see if we now apply the convolution to this zero padded image, now the output has the same size as the input. So because the convolutional kernel fits in each of these positions, and therefore the output will have the same size as the input. So zero padding allows us to keep the same spatial dimensions, so width and height. And now our key question is, shall we zero pad or not? And essentially this is a design choice. So if we don't zero pad, this plays well with the idea of ConvNets, and the idea of ConvNets is essentially just transform your image into more and more abstract feature maps. So the lower layers are essentially designed to capture low-level features like maybe edges or something like that. And the higher layers are intended to capture more semantic features or high-level features. And if we don't apply padding, then we are essentially reducing these feature maps, and which essentially means that we are compressing information into fewer and fewer features. So not zero padding will reduce our features, which might be a good thing. On the other hand, it's really hard to keep track of all the image dimensions. So if we apply different kernel sizes to different layers, then it's really hard to keep track of all these different dimensions. So the typical thing is actually that you do zero padding and that you essentially keep with the same dimensionality. However, it's still a good idea to reduce features, but what people typically do is pooling. So downsampling or pooling to reduce the number of features. So pooling or downsampling reduces so downsamples our spatial feature maps. And so in principle, this works pretty similar to convolution. So we also have a sliding window sliding over our feature maps. But pooling, rather than doing this linear combination like in convolutional layers, aggregates the values in a window to a single value. So, and it does so by applying some aggregation function, and the most common used aggregation functions are maximum, and then this is called maximum pooling, or taking the average, and then this is called average pooling. And now, so pooling has hyperparameters like the window size, called KP, and a stride or hop size called SP. And so if we have multiple channels, then pooling is just applied independently for each channel in the feature map. So let me give you an example. So for max pooling, so let's see how max pooling works, and we are looking at this input image, or at this input feature map. So again, we are only considering one channel, and we are using a pooling window size of 2 and a stride or hop size also of 2. So how does this work? So we start with our window on the top left. So we are using a 2 times 2 window. So the window size is 2. And so we are considering max pooling. So we are looking for the max in this window, which is 4. Therefore, you copy a 4 here. And with a stride or hop size of 2, so we move the window by 2. And now we looked at the maximum. This is 3, so we copy a 3 here. So now we've arrived on the right-hand side, so we just hop 2 pixels, so stride 2 pixels down, and again to the left. And here again the maximum is 5, so we copy a 5 here. And again we move 2 pixels, and we get the maximum 3 here. And this is the result. So if we apply max pooling with window size 2 and stride 2 to this input, this is the result of max pooling. Let's also look at average pooling, but with different parameters. So let's now consider a window size of 3 and a stride or hop size of 1. So we start again in the top left corner. And so now we apply average pooling, so a different aggregation function. So we take now the average of these values. And if you compute this, you will find that this is 2.55. And we move now the image with a different stride than in the previous example, so just by 1. So we move it by 1 pixel. And now again, if you compute the average here, you will see that this is again 2.55. we've arrived on the right hand side. So we move 1 pixel, because the stride is 1, down and again to the left. And if we compute the average here, you will find that this is 2.33. And again, we move by 1 pixel, and you will again find that the average of these numbers here is 2.33. And this is the result of average pooling for window size 3 and stride 1. Okay, so we've discussed now convolutional layers and pooling layers. And the whole idea of convolutional layers is that we get like this more and more abstract features. Sometimes we apply pooling to actually downsample the features. And yeah, so the idea is that this stack of convolutions and pooling abstract more and more abstract and or semantic features. But at some time we want to perform machine learning, so like for example classification or regression or whatever. So we just want to have back our feature vectors, and essentially this is pretty simple. So at some point, say we would get a feature map, maybe output of a convolutional layer of 24 times 24 times 8. But then all we need to do is just unroll this feature map into a vector. So 24 times 24 times 8 yields 4,608 different features. And so essentially we just roll out this three-dimensional tensor again into a vector. And now, for example, we could use this vector and apply some fully connected layer. So essentially a multi-layer perceptron on top of this. And now, this already concludes this section. So we've discussed in pretty much detail convolutional layers, which just transform two-dimensional feature maps with multiple channels. In other two-dimensional feature maps, also with multiple channels. We discussed zero padding, so if we want to keep the same spatial dimensions in convolutional layers. We discussed pooling, which essentially is downsampling with different aggregation functions, max pooling or average pooling. And in the end, so if we want to go back to multi-layer perceptrons, then we can just flatten out our convolutional features and work with multi-layer perceptrons on top of this, or with fully connected layers on top of this.